Hello, AP Stats students. We're going to be starting chapter 3 today. This is actually our last chapter. It will be part of what's on the AP exam, at least it could be. Make sure you're looking at how the AP exam has changed. We put a few posts out there in Classroom for you to look at. You'll have a packet put on this Classroom post as well. So if we'd been in class, you would have received the new chapter 3 packet. You may want to be looking through that. Print it if you can, or otherwise just have it open as a PDF file so you can look at it. Chapter 3 is all about describing relationships. We're looking at what's called scatterplots. I know you've seen scatterplots many times. We're going to be looking at how those work, how we describe them, and how we create them. So some of the main things that we'll be doing here in this section, I'm going to highlight some of them. When we look at a scatterplot, there's always two variables, something called the explanatory and something called the response variable in every situation. And so we want to be able to identify those. We also want to be able to make the scatter plot, do it on our calculator. Everything that we do with scatter plots, it always is quantitative variables. So it has to be two variables that you can measure. They cannot be categorical variables. And then what we'll finish with in this video today is how you describe a scatter plot. We'll talk about being able to look at a scatter plot and describe the strength of it, the linearity, does it follow a straight line or is it some sort of a curve? And then what's the association within that relationship? And as always, we'll look to see if there's anything kind of weird, anything unusual, like potential outliers on the scatter plot. In another video, we'll do the rest of these things down here. So here we go. Here's our first example. The question says, is there an association between a car's horsepower and its miles per gallon rating? Let's take a look at the scatter plot. So here's a scatter plot showing a scatter plot of a lot of cars. Every dot here is a car. So there's a car right there. There's another car. Here's another car out here. We've got a bunch of cars. We're looking at the horsepower of the car versus the miles per gallon. And we can see there's a general relationship that's showing there. It kind of looks like when we look at the scatter plot here, we'll talk about what's the association between the two variables. So association, I want you to notice this. It looks pretty clear that the general trend of these points sort of follows this kind of a curve. And it's a downward curve. So it looks like as the horsepower of a car is increasing, as you're getting more and more powerful engines, it looks like the miles per gallon is actually going down. That might make sense to you if you know anything about cars, because cars that have a lot of horsepower are typically, they're very powerful cars, maybe big pickup trucks, things like that, and they generally do not get good gas mileage. What you might have up here, cars that are out here would be cars that are not very powerful, so they're probably pretty small cars, but they're going to get very good gas mileage. When we look at how strong the association is, we're going to be looking at, do the points on the scatter plot follow a pattern pretty closely? And when I look at this, I think this looks very strong. It's not like I see a lot of scattered points where there's cars all over the place like this. We follow a pretty good pattern and form here. As far as anything unusual, I don't see anything looks too unusual. If you're looking at these and thinking, well, these cars out here might be unusual, yeah, they're kind of separated from the other points, but on the other hand, they do sort of follow the pattern. So I would say they're not too unusual because they follow the pattern. Something unusual might be a car, like if we had a car way up here. That would be unusual because it's definitely off of the pattern. That would be a car that would be extremely strong in horsepower and also get incredibly good gas mileage. I wish I had a car like that. I do not. So one of the things we need to look at too is, what are the two variables? We always want to be able to identify the two types of variables that are at play on a scatter plot. And those two types have names to them. One of them is called a response variable. That's the one that it says measures the outcome of the study. The other variable is called an explanatory variable. The explanatory variable helps to explain what's going on up in that response variable. So if we look back at our horsepower problem here, mileage versus horsepower, which one is the explanatory variable here? I would say the explanatory is horsepower. And notice the horsepower is on the x-axis. The explanatory variable is always going to be on the x-axis. I think horsepower is explaining what's going on in terms of the miles per gallon. So the response variable here is miles per gallon. So response is always on the y, explanatory variable is always on the x-axis. So to kind of describe in general what's a scatter plot, it says up the top, a scatter plot shows the relationship between two quantitative variables that are measured on the same individual. The values of one variable are on the horizontal axis, that's our explanatory variable. The values of the other are on the vertical axis, that's our response variable. And every individual in the data appears as a point. So here's a different scatter plot. Now we're talking about cities that are in the state of Nevada, and we're looking at their elevation versus their mean annual temperature. So every city is just showing as a single point. So we've got whatever 30 or 40 cities plotted here, and we're looking at their elevation versus their mean annual temperature. So when you make a scatter plot, you should think about what variable is going to go on the axis. And to do that, you need to think about which one you think is the explanatory variable. I think it makes sense here that elevation is being used as the explanatory variable because how high up or down in elevation a city is probably has a pretty big impact on its temperature. So the explanatory variable here I think makes sense to be elevation, so it's going on the x-axis. And then the y variable is our response variable, be the mean annual temperature. And it is important, I know in the AP exam, they make a big deal about if you were to create a graph of any kind, a graph, a scatter plot, we've talked a lot about this in class, that you should always have it labeled. So it's important to label your axis, scale the axis, put the values on it, just so somebody can look at it and understand completely what it's talking about. And then you would plot the individual values, the individual cars, the individual cities in this case. So here's something you could do if the AP exam asks you to make a scatter plot. This is how you would lose points. And this is from one of my favorite comic strips, XKCD Comics. If you want to look it up, you can go to xkcd.com and you will find a lot of them. We put some of them in our packets. So here's how you can lose points. So here's a guy and a girl that are dating. The guy says, I think we should give it another shot. She says, we should break up and I can prove it. How would she prove it? She breaks out a scatter plot of the relationship. There's a definite downward trend. It does not look good for this couple. The guy looks at it and says, huh? Maybe you're right. She says, I knew data would convince you. And he says, no, I just think I can do better than someone who doesn't label her axes. Ooh, big statistical burn, burn, burn. The point is, you should label your axes. Don't forget to label them. All right, break out your calculators. If you don't have them out yet, you're going to need them here. We're going to try and make our first scatter plot on your calculator. So we're looking at something here on a track and field day, and it says the table below shows the data for 12 students in an AP Stats class. And we had each of those 12 students do this. They ran a 40-yard sprint, and we recorded their time in seconds. Then they did a long jump with a running start. And we recorded their long jump distance in inches. So the question is saying, can we just make a scatter plot of the relationship between sprint time in seconds and long jump distance in inches? So if you have your calculator out, here's what we would do. I would tell you in list number 1, put all of your sprint times. In list number 2, put all of these long jump distances. And I'm going to go ahead and get my calculator out here too, so that you can see what we're doing. And I think, pause for a second here. I need to share to you the whole screen. Here comes the calculator back up. So you would be going to Stat Calc, and you'll notice I've already typed in all the data here. You can pause the video if you want to right now and enter your own data in. And then I'll show you how I'm going to do it. So pause for a second, type your data in, and then come back to me. So I've got all my data in. How am I going to make a scatter plot out of that? So I'm going to quit out of this, and I'm going to go to stat plot. Same place we've always made histograms, normal probability plots, box and whisker plots, all those things. I'm going to make sure I go into plot number 1. I'm going to make sure it is turned on. And then the type of plot you want to do is the very first one there. I'll get off of it so you can see it, but it looks like just a series of points. So make sure that is chosen. Make sure you've thought about what your X list should be. That should be your explanatory variable, and what your Y list should be. I think it makes sense here that the sprint time might help to explain how long somebody can do the long jump. Because if they're running up to do the long jump with a running start, obviously the faster you can sprint could obviously help explain how far you're able to jump. So I'm going to put my sprint times in list 1, my jump distances in list 2, got it set up. I'm going to quit out of that, and I'm going to do zoom 9 to have the calculator pick a good window for me. So zoom stat, and here's our scatter plot. So you may want to make sure you can have yours showing. While yours is showing, I'm going to go ahead and hit trace, and I want you to notice that when you hit trace, it puts a little star on single points, and it kind of flashes them a little bit, and it'll tell you the X and the Y values for those. So if I arrow right and left, it'll move to different people in this case. If you're wondering how come that little flashing star is jumping all over the place and not just going from one to the next to the next, what it's doing is it's going in order according to the way that you typed it in. But there's our scatter plot. All right, so let's get back to looking at this. You can keep that scatter plot on your calculator. And I do have a slide in here that shows you how to put this in. So if you need to come back to it, you can look at this. But as always, your textbook shows you in detail how to do anything on the calculator. But you can look at this as you need to. So now we know how to make scatter plots. We're going to take a look at how you describe them. So when we describe a scatter plot, it says we're going to follow our basic strategy of data analysis we did back in chapter 1 and 2. We're going to look, are there patterns, and we're going to look for departures from the pattern. So when we examine a scatter plot, we're going to describe it by using these 4 basic things. We're going to talk about the strength of the scatter plot, the linearity of it, in other words, how well does it follow a straight line, and the association of it. And we'll talk about each of these here. But we'll also look to see if there's any points that are outliers. That would be a departure, where there's some point like that weird car that I drew on the scatter plot that doesn't really fit the pattern. It falls outside of the overall pattern there. So this is going to be sort of like socks. Remember when we had histograms before, or any distribution, we'd talk about socks. We would say you got to compare the shape, any outliers, the center, and the spread. And again, the order we do these in doesn't matter. We're just giving you acronyms that make a word for you so you can follow them, but the order you describe it in doesn't matter. So let's talk about these 4 things that you need for scatter plots. This is not going to be socks. So we're going to talk about the strength. How closely do the points follow the form? If those points, there we go. Okay, if those points follow a pattern, I'm going to try and draw a small one right up here. If they follow a pattern really well, then it's pretty strong. If you have a scatter plot where those points are all over the place, they don't really seem to form any pattern, then it's pretty weak. So here we have a small example of a strong scatter plot. Here's a weak scatter plot over here. Second thing we want to look up is the scatter plot linear. And we're either going to see scatter plots that are roughly linear, or we're going to say they're not linear, meaning they have some sort of a curve in them. The third item, association. Association we're going to describe as either positive or negative. And what we'll be looking for with association, I'll draw you a quick example of one. This is for association. If it's positive, the scatter plot is moving upwards to the right. If it's negative, sorry those lines keep drawing, if it's negative, the scatter plot is moving downwards to the right. And when we talk about association, we always want to include the context of the problem. You'll see how we do that as we go on. but positive means upwards to the right, negative means downwards to the right. So let's see, I'm going to get rid of all those drawings so they don't overlap our scatter plot. Okay, so here's our scatter plot of the sprint times versus long jump distances. We also want to look to see if there's any what we would call points, any outliers or clusters within the data. So if I was going to do this, if I was going to describe the track and field scatter plot up here, talking about these 4 characteristics above, here's what I would say about each one. I'm going to verbally say this, but we'll see some other ones written out. In terms of the strength, I'd say that scatter plot is fairly strong. Those points tend to follow the pattern pretty well. I don't see points that are scattered all over the place. Now, could it be stronger? Yeah, if these points were closer together, that'd be stronger. But I don't see anything, it doesn't look, really weak to me where there's points all over the place with no real pattern. Is the scatter plot linear? I'd say it's pretty linear. The scatter plot is roughly linear. It follows roughly a straight line. It's never going to be perfect, of course. And then for the association, here's where I'm going to mention positive or negative. This association is definitely negative. And so if you keep track of what that means, remember we had time down here and we had long jump distance as the y-axis. So I would say something like this: the association is negative. What that means in context is this: as a student's sprinting time increased, which, remember, if their sprint time increases, that means they're actually slower because they take longer to do that 40-yard dash. So if the student's time is increasing, their distance that they were able to jump is going down. So as time goes up, distance generally goes down. And if I look at the last thing, is there any unusual points anywhere, any unusual departures? When I look at the points up here, all 12 of them, I don't see anything that looks really out of the pattern here. I don't see anybody that is incredibly slow but could jump really far, like that point would be. And I don't see anybody that's super fast, that would be down here, but has a terrible long jump. Everybody's kind of following in this pattern here. There's nobody that's really off of the pattern. Now, you may be asking yourself, what would be a good acronym to help me remember this, Mr. Lofgren? If only there was some way I could remember strength, linear, association, and points. I think you know what's coming. We will talk about SLAP. So when we describe a scatter plot, we're going to use the acronym SLAP to help you remember to talk about the strength, the linearity, the association, and points. So let's look at another example, totally different context here. We're talking about McDonald's here. I'm still loving it. The scatter plot shows you the amount of sodium in milligrams and the amount of fat in grams for 10 salads from McDonald's without any dressing. And it says describe the relationship between sodium and fat. Well, if you look at this, I think you might see something that kind of stands out here initially. There's something that looks just a little different about this scatter plot. And yes, we're going to talk about the strength, the linearity, the association, and any unusual points. But I want you to see that what's going on here is that there's actually clusters of data. So when you look at this, I hope you see there's 3 kind of groups. 3 groups of these chicken sandwiches. I'm going to kind of get a laser pointer to help you see here. So we kind of have a group down here. We got another group of 3 right in here. And then we got a group of 3 up here. And we want to try and understand, if we see clusters, try and think about why that is happening. There's actually a really good explanation for why this is happening. The salads that McDonald's sells have chicken on them, sometimes. So these 3 clusters that we look at, here's what explains them. The salads down here in the green that have pretty low sodium and pretty low fat don't have any chicken on them at all. The salads in the blue have chicken that's been grilled, and the salads in the red have fried chicken. So the fact they're fried maybe makes sense now why they have more sodium and also a lot higher fat content. So if we go back to describe this now, let's talk about the strength. I would say within each of these clusters, it looks pretty strong. The points follow the pattern within each of the clusters. I would also say each cluster is roughly linear. Again, with only 3 points, they follow that linearity pretty closely. Again, sorry for that extra line down there. For association, each of these is positive. As the sodium goes up, the amount of fat tends to go up too. And that's happening with each of these. As the sodium increases, fat is tending to go up too. Anything unusual here? I don't really see anything that looks too unusual. No points that are kind of following off the pattern. But what's definitely unusual that I would want to mention is what we've already talked about, the fact that there are clusters, that it appears that there's 3 clusters. So we've been talking about this idea of association here. Let's try and clear this up a little bit more. When we look at the 2 variables on the scatter plot, we're going to say that there is a positive association when above average values of one variable tend to accompany above average values of the other. And below average values of one tend to go with below average values of the other. So I want you to notice this. I think my video might be covering these arrows up, but they're both going up. So they both go in the same direction. That's positive. If you have a negative association, that's where you see one variable goes up and the other one goes down. And it doesn't matter that it's the x going up with the y down or the x going down with the y up, but they're moving in opposite directions. So I'm going to show you one more example, again, a totally different context here. This is looking at the 50 states. So every dot here is a state. And what we're looking at is the percentage of students in that state that take the SAT. Notice it says SAT, not ACT. So this is your explanatory variable. And then the average, the mean math score on the SAT, this is your response variable. So we're trying to use the percentage of students taking the SAT in that state, in each state, to help explain what's the mean math score. So when you look at this, you might see that it looks pretty strong. The points follow the pattern fairly closely. Again, it's not perfectly strong. So it looks fairly strong. I would definitely say that it looks like there's a negative association, because it looks like as more and more and more students percentage-wise in a state are taking the SAT, pretty clearly the average math score in the SAT test is going down. When you have few students taking the test, like these states up here, they tend to score pretty well. When you have higher percentages of the state or of the students taking the test, they tend to score a lot lower. So the association is negative. Do we see any unusual points, any unusual outliers? This one could be. That's a high percentage of students taking it and a pretty low test, average mean math score. That kind of looks like it breaks out of the pattern. Some of you might think this one also breaks out of the pattern a little bit. So if I was to describe this, here's how I described it. I said there's a moderately strong and negative curved relationship. So I want you to notice in here, just in that one sentence, I took care of strength when I said moderately strong. I took care of association when I said negative, and I took care of linear when I said it's not linear, it's curved. So there's a moderately strong negative curved relationship between the percentage of students in a state who take the SAT and the mean SAT math score. I also said, hey, here's some unusual points happening. Looks like there's 2 distinct clusters, kind of like our McDonald's salads. And to help you see that again, I'll erase all the ink I've drawn on here. It looks like there might be a cluster of states kind of here, maybe another cluster of states happening down here. And I already mentioned the couple possible outliers, maybe here, maybe here. I'm just saying, notice I said they're possible, not saying for sure, I'm just saying possible. But what would explain these clusters? Kind of like we talked about the chicken explaining the McDonald's. Well, I think a reasonable explanation for this is this. Think about states like Iowa. And if we were in class, I'd ask you how many of you have taken the SAT, and I bet most of you have not. But think about who in Iowa does take the SAT. Most of us don't because we take the ACT here. So who are the students that take the SAT? Probably they're students who are looking at going out of state, potentially pretty far out of state, and looking to go to maybe some of those better colleges, you know, those like Ivy Leagues and things like that that are on the coast, West Coast, East Coast of the US. So students that look at doing that, they're probably typically better students. So they might score higher on average on their math test versus states where most of the students take the SAT. Well, anytime you have most of the students taking it, you've got the better students, you've got lower scoring students, and everybody in between. So that brings your average down. So I think that could help to explain what's going on here. So notice I'm describing this. Here's my strength statement. Here's my association statement. And here's my statement about linearity, or the fact that it's curved. So let's look at our final one here. One last context. Describing scatterplot. This is all the teams in the SEC conference. And we're looking at, in terms of their football games here, we're talking about how many points they scored per game. That is our explanatory variable again. We're using your points per game to explain how many wins the team's got. So if we were to describe it, I'll pause here. You might want to try and describe this yourself, at least say it out loud to yourself. Can you talk about the strength, linearity, association, and any unusual points you might see here? So pause it, try and describe that for yourself. And then I'll show you what I wrote. So here comes my description. For association, I said in general, it appears teams that score more points per game have more wins, and teams that score fewer points have fewer wins. So that's a positive association. As points per game goes up, your wins per game tends to go up too. Probably not a surprise. If you have a team that scores a lot of points, they tend to win more. And that's a positive association. In terms of linear, I said, yeah, there's a pretty rough linear pattern here. It doesn't really look curved. It looks pretty linear here. It roughly follows a straight line. In terms of strength, I would say this one is really strong actually, because those points do follow a straight line pretty well. So they follow that. I don't see any unusual outliers. So I'm taking care of the P idea there. There's no obvious outliers here. I would have you think about what would you know about a team like this. If there was a team that was up here, think about what might explain a team like that was a serious outlier out there. They don't score many points at all. They're pretty low on points per game, but yet they have a lot of wins. Think about how that could happen. If you don't score many points, but yet you win most of your games, probably the explanation for that is that you have a great defense, that you're not letting the opponent score many points either. On the other hand, if you had a team, picture an outlier team down here that scores a huge amount of points, but yet they hardly win at all, I'd probably say their team has a terrible defense. Because even if they score a ton of points, but they're losing most of their games, the other teams are scoring more. So we want to be able to take any scatter plot, describe the strength, the linearity, the association, and any unusual points. And with that, we're going to stop this video here, and you are ready for homework number 1 in chapter 3.